Hey guys, so this is supposed to be our first lesson back for term 2. We finished chapter 5 during the holidays, or you should have done that anyway, so I'll be checking your work soon, which you should be posting on the OneNote document, which is on our team. But yeah, 6A for now. So 6A is the language of polynomials, as you can see up the top there. And basically what we're going to be doing at the start is just going over what some specific words mean in some of the questions that you'll be seeing. Because if we don't understand the words in the question, how are we going to be able to answer that question properly? So there's a few terms here that we're going to go over. So polynomial function's one of them, then leading term, then the degree of a polynomial, and then a constant as well. So some of you guys might already know what some of these words or terms mean, but we'll go over them now anyway. So a polynomial function, as I've got written down here, it's a function that's written in this form. Now this form here, it might look a little bit confusing, but the example should make it a little bit easier for us to understand what it is. So you know how we've had like square root functions and hyperbolas, we've had truncus as well. None of those functions look like this. This one here is a polynomial function though, because we've just got our x to the power of 3, whatever our highest power of the term is, and its coefficient there, and then we go down to the next one, which is x squared, then x, and then you've got your constant as well, which we'll talk about pretty soon. But it's basically going to look like this all the time. They might be x to the power of 4, it might be x to the power of 5, any number going down. Okay, now one thing as well, it doesn't have to be in a specific order. So if I move this 5x to the power of 3 over to the end, it's still a polynomial function. It's just that we've rearranged the order of those terms and it doesn't actually change anything. Okay. All right. Now, one of the things that we need to know is the leading term. And as it says here, it's a term with the highest index or the highest power. So if we look at this one here, g of x, we can see that we've got an x squared, we've got an x cubed, x to the power of 1. So the highest power is this 3, isn't it? So it's the term that has that highest power, which is this one. So 5x to the power of 3 is our leading term. If we look at this one here, I want to find our leading term for that one. So we can see there's our highest power, so this must be the leading term for f of x as well. Okay? All right, let's go down to degree. Now, to know what degree is, we need to know what leading term is as well. So the degree of a polynomial is the power of that leading term. So if we look at this example here, h of x, we can see that 3 is our highest power. So that means the degree is 3, as it says written down here. If we look up at g of x, 3 is our highest power here as well, isn't it? So the degree of that one will be 3. And if we move up and look at f of x, look through these terms, this one here has the highest power of x, so the degree would be that power, which is 3. Yeah? All right, now the last thing we need is the constant term. Now, as it says here, that's the term that doesn't involve x, it's just the term that's your normal number. Okay, so if we look through this one, that's got an x, so that can't be our constant, that's got an x, that's got an x, this one doesn't. Okay, so there's our normal number, our constant for this example is 1. If we look up at this rule here, I want to find the constant. We started off with the constant here because see this 15, it doesn't have an x assigned or attached to it, so our constant would be 15 there. If we look at g of x, this example, we can see that the only one that doesn't have x involved is this 7, so that is the constant. And the last one up the top here, see how we've got an x, x, x. This one here doesn't have an x, so our constant is 6. So before we move on, let's just make sure we can kind of answer questions or identify what our leading term is or our degree or what our constant is as well. So let's just have a go at this question. It would probably be a good idea if you pause it right now and try and do it yourself. I'm going to do it right now though. Okay. Okay, so leading term is a term that has the highest power. I can see that I've got to the power of 3, to the power of 2, to the power of 1, so 3. is our highest power. The leading term is that whole term though. Okay, so the leading term is going to be 8x to the power of 3. Now the degree, if we remember from before, and I'm going to go up a little bit, the degree is the power of that leading term. So we already worked out that the leading term was 8x to the power of 3. The degree is that power, so the degree is going to be 3. And we need the constant as well. So the constant was the term that doesn't have x. There's an x there, there's an x there, there's an x there. This one doesn't have x, so our constant's going to be 1. And we're finished. So let's do the next one now. Again, try it yourself. This one, well, if we compare these two, this one was ordered really nicely. Now, whenever you write a polynomial function, one of the things that people like to do is they order the powers. So you'll start with like to the power of 3, then to the power of 2, then to the power of 1, starting from the highest and going down. This one here hasn't been shown to us in that way. See how we can see x to the power of 1, then x to the power of 3, then x to the power of 5, then our constant, and then x to the power of 1. It doesn't matter what order these are in, we still should be able to find our leading term, our degree, and our constant pretty much the same way. So I'm going to do that now as well. Okay, leading term, so the term that has the highest power. I can see that we've got x to the power of 3, but is that the highest? No, I can see there's a higher one here, which is x to the power of 5. So this whole term here is our leading term, 2x to the power of 5. The degree is the power of the leading term, so the degree is 5. And the constant is the term that doesn't have that x involved. So if we look through here, we can see that x isn't involved here. So that's our constant. Done. Alright, so there's a couple more examples that I want to do before I let you go to do the questions for 6a. So some parts of 6a involve a little bit of expanding. Now, you've seen stuff similar to these before. I think we have actually expanded with to the power of 3 here before, but normally what we've done so far this year is we've just had a squared there. So I just want to make sure that we know exactly how to do it no matter what the power here is. Now, what I'd like to do is just write this in a little bit of a different way so we can kind of see what it means. Because if we have, for example, let's just say the number 4, and we have that to the power of 3, that actually means 4 times 4 times 4. And it's the exact same thing over here with this example. So you could also write this one here as a plus b times a plus b, times a plus b. Now, with it in this form, and we want to expand it, don't we? Because that's what the question's asked for. You guys know how to do FOIL because you've done it for a few years now. What I'd suggest you do is just forget about this last term for the time being and just expand those two out. We can worry about that last term a little bit later. So that's what I'm going to do to start with. Actually, I'll do the line so you can see what I'm doing. So remember, first, outside, inside, last. There you go. So you've done your FOIL expansion for those two, but we still need to expand this out even further. So with this one up here, when we're doing FOIL, we just made sure all the terms in the first set of brackets were times by all the terms in the second set of brackets. That's what we're doing here as well to further expand this out. So everything inside this set of brackets has to be times by everything in this set of brackets. So I'll start with a squared times a, then a squared times b. Then I'll go to the next term. 2ab times a, 2ab times b, then go to this last term, b squared times a, b squared times b. And I'm going to collect all those like terms, which I'll do right now. Okay, so I times everything inside here by everything inside here, and now I'm going to collect those like terms. With the cubes and squares everywhere, we need to make sure we know which ones can actually go together. So if we look at this one here, a squared b, this is only going to be able to go with anything else that's also a squared b. So this one is also an a squared b, so we can put these two together. Same with these two here. This is an ab squared, another ab squared. We can put those together. There we go. So I've completely expanded that one out now. Now this is actually a rule. I'm going to put a box around here. You don't necessarily have to definitely remember this one, but it can make life a little bit easier later on. Instead of doing all these steps here that I've gone through, if you can remember this rule, you're going to be able to expand out anything that looks like this. So you've got two things inside your brackets which are cubed really fast. So there's another example over here. We could do it with this process, but I'm going to try to save time, so I'm going to use this rule just here. Now remember, that's our A. See how there's A's there? That's our B. See how there's B's in here? So if we look at this one here, this is going to be our A, and this is going to be our B. All we need to do is take those values and put them inside this rule, and it's the expanded version. It's going to be a lot quicker. So I'm going to substitute them in right now, and we'll see if it's a little bit faster. So I've substituted them all in. All I want to do is just kind of simplify this now. So 27. And we're done. Finished. So you see how that was a little bit quicker than trying to use FOIL. Now you can use FOIL and go through this process, it's fine. It's just that if you want to be nice and fast, this might be a better thing for you to do. Up to you. Okay, so the last part of this exercise here is going to be equating coefficients. Now in the blue here, it's a really brief explanation of what you're actually doing. So I'm just going to read it out. It's a way of solving for unknowns given that two functions are said to be identical. So if we look at this example here, we're being asked to solve for A, B, and C, so A, B, and C, by equating coefficients. So it's set up here that the two functions are said to be identical. That means we've got this rule here. It's supposed to be identical to this rule here. The only problem that we have at the moment is that they're in a couple of different forms. So this one here is expanded out. This one here, it's not actually expanded out, is it? It's factorized a little bit. Okay, so what I'm going to try to do is try to make both of these sides look the same, and then I'll be able to work out what A, B, and C are. So I think the best way to do this is maybe I'll expand this side out, because then it should look exactly the same as that, and then it might be easier to identify what our A, B, and C values actually are. So I'm going to use this rule here to expand this out, but remember I'm going to have to times it by A as well at the end and add C too. So I'm just going to go through that process right now. It'll probably be a good idea if you try to do it yourself as well and then checked your answer at the end. one. Okay, so I use the rule up here to get that, but as you can see, we still need to times everything by a, and then we have the plus c at the end as well. So that's the next step of what I'm doing. Okay, there we go. So we have, or I have expanded that out now. So given that they said this, which is the same as that, because this is just the expanded out version, is equal to that, that means that this should also be equal to that. So I'm going to put that in here. Okay, so we can see that the coefficients over here, so the coefficient of x cubed is 1, the coefficient of x squared is 3, the coefficient of x is 3, and then our constant is 8. Over here we've got all these a, b's and c's, don't we? But I just want to show something. You see how we have x to the power of 3 here, and the coefficient is 1. We've also got x to the power of 3 here, and the coefficient is a. If these are the same thing, that means that this one here has to be the same as that a there. So that means a is 1. We've already got our first answer. So a equals 1. Now the next bit, I'm going to look at my x. I'll use a different color actually. I'm going to look at my x squared here. See how the coefficient is 3? I'm going to look for my x squared over the other side. So there's no x squared here. No, that's just normal x. Here's an x squared. So this is what I'm looking at here. Now, that means we have 3 times a times b has to be equal to 3, because that's the coefficient on each of these sides here. So that means 3ab has to be equal to 3. Now, we already know that a is 1, so we can change that to 1. So that's going to give us 3b equals 3. So b is also going to be equal to 1. Awesome. The last thing we need to do is find out what c is. Now let's look over here. See how c is just there? Now it says that the constant is 8. Now the confusing thing about this part is this is the only part that doesn't apply to any x. There's no x with it there. This doesn't have any x either, but this doesn't have any x either, does it? Okay, so it's actually all of this section is equal to 8. So we're going to have a, b to the power of 3 plus c equals 8. Now we know what a is, it's 1. We know what b is, it's 1. So if we plug that in there, we're going to have, I'll do it. 1 times 1 times 1 times 1, which is 1. So that gives us 1 plus c equals 8. So c is going to have to be 7. And we're done. There's our answers. So that's it for 6a. You're also going to have to do 6b as part of this question. So I'll get you to move over and start that video now.